Hello my friends, in this video we will be going over 2000 AIME 2 problem number 15. Here's a view of this problem. We would like to find the least positive integer n for which the left hand side summation expression is equal to 1 over sine n. I will go ahead and apply my sine 1 trick. I will multiply both sides of this equation by sine 1 degrees, and as a result I would have the following expression, right? So on the left hand side, each of my numerators will have a sine 1 degrees, as well as the right hand side. But now the trick is to rewrite one as, in this particular case, 46 degrees minus 45 degrees, and this one as 48 degrees minus 47 degrees, and so on. So in the generic case, we would have sine 1 over sine, let's say, x times sine of x plus 1. That whole thing would be equal to sine x plus 1 minus x divided by sine x times sine of x plus 1. But now we are in good shape. I know by the difference formula for the sine function that I would have sine of x plus 1 times cosine of x minus sine of x times cosine of x plus 1, all divided by sine of x times sine of x plus 1. Now when you focus on the first component, the sine of x plus 1 would cancel out. We would have cosine x over sine x, which is simply equal to cotangent x minus, and here the signs will cancel out, and I will be left with cosine of x plus 1 divided by sine of x plus 1, which is simply cotangent of x plus 1. Now I know exactly what to do. The whole left hand side of this expression here, so the left hand side would simply be equal to, so from the first expression I would get cotangent of 45 minus cotangent of 46, plus from the second one we would get cotangent of 48 minus 47, I should have said, 47 minus cotangent 48, and let's write one more, cotangent of 40, so the next one would be 49 minus cotangent of 50 degrees plus, and then we will have cotangent of, in the previous term it would be 131 minus cotangent of 132 plus finally cotangent of 133 minus cotangent of 134, and we need to confirm this whole expression is equal to sine 1 over sine n, and from there get the n. Okay, so that whole thing would be equal to, after reorganizing in the following fashion, let's keep this one by itself, so we have cotangent of 45, and what I would do it would be the following. So minus, I have the cotangent 46, I will pair it up with cotangent of 134. Both of them has a minus sign in front, so I would get cotangent of 46 plus cotangent of 134. And I will do one more example. In a similar way we would get for example, I would get cotangent of 47 here with a plus sign, and I will pair it with the plus sign cotangent of 133. So I would have cotangent of 47 plus cotangent of 133, and so on. So as you will see, the signs will alternate, so the next one will have a minus sign here. If I keep going all the way I can go all the way to cotangent of, when I do the last terms, the ones in the middle will be, oops, let me rewrite carefully. So I would have cotangent of 89 plus cotangent of 91 degrees, and finally we would have a minus cotangent of 90 degrees by itself. Okay, but now that's perfect for me because, well, cotangent of 46, cotangent of 134, cotangent of 134 is just minus cotangent of 46. They would cancel out. Cotangent 133 is just minus cotangent of 47. They will cancel out. And similarly for these two, all I'm left is cotangent 45 minus cotangent of 90. I know cotangent of 90 is simply equal to 0, so therefore the whole thing reduces to cotangent of 45 degrees, but I know very well cotangent of 45 is simply equal to 1. Now I know this left hand side should better be equal to this right hand side, so therefore it would imply this 1 is equal to sine 1 over sine n, and this would simply imply that sine of n is equal to sine of 1, and therefore we would say that the least positive integer value for n would simply be equal to 1. And that solves the problem. Hope to see you guys in our next video.